Now, covalent bonds form when atoms share electrons to complete their octets. And these are only going to be between non-metal atoms, so there won't be any metals at all. And that's how you know that it's going to be covalent bonding. So remember, using the periodic table, that staircase separates the metals from the non-metals. Let's start off then with hydrogen. Two hydrogen atoms would have one dot for electron dot symbols, so they could share these two electrons. And we replace the shared electrons with a dash, that's the covalent bond. And this gives us a hydrogen molecule. Hydrogen is just trying to become like helium, so in this sense, each hydrogen atom has gained an electron for part of the time, and thus they are more stable. So a hydrogen molecule is more stable than a separate hydrogen atom. In fact, on this planet, we don't have any separate hydrogen atoms. Pure hydrogen is all in the form of hydrogen molecules. Let's look at another one. We can take two fluorine atoms. Now, each fluorine atom has 7 valence electrons. So they can share the unpaired electron. They will share these two electrons. That's our shared pair. So that's going to be our bonding pair. And these other guys around here are our lone pairs. And so that bonding pair can be replaced by a dash. There we go. And there is our fluorine molecule. So in these molecules, we're going to have lone pairs, and we're going to have bonding pairs. So here are fluorine again, and here's oxygen and nitrogen. So here's our fluorine atom. They're sharing one pair of electrons. Now if you look at the oxygen, 2, 4, 6, 2, 4, 6, oxygen atoms need 2 electrons. That's why these two unpaired. So they can share both of those pairs of electrons. And for nitrogen, nitrogen has 3 unpaired electrons. It can share all 3 pairs. And thus we wind up with a single, a double, and a triple covalent bond. And then we put in the lone electrons. So in summary then, this fluorine atom has 2, 4, 6, 8. This fluorine atom has 2, 4, 6, 8. This oxygen has 2, 4, 6, 8. This guy has 2, 4, 6, 8. Okay. Now how many lone pairs of electrons? Well, we're looking at them. 6, 4, and 2. Now these are the elements that exist in nature as pairs of elements. There are 7 of them. And so anytime you are asked to write the formula, like for nitrogen, you write down N2. You would just ask for the symbol, you say N. So these guys have symbols and formulas. So remember we just did it a moment ago. One bond between the two hydrogen atoms, a triple between the nitrogen, a double between the oxygens. Now the other guys all have singles. And you notice that these 4 here are all in the same family. So let's check out water, and we can see why is water H2O and not HO or H3O. So if we start off with an oxygen atom, here's its electron dot symbol, and we bring in a hydrogen over here. That's going to be one bond. We bring in another hydrogen from the bottom. It'll give us our second bond. And then we draw the structural formula. So this way each hydrogen has the 2 electrons it's looking for, and the oxygen has 2, 4, 6, and 8. So that we wind up with then 2 lone pairs of electrons and 2 bonding pairs in H2O. So using electron dot symbols, we can come up with the reason why water should have the formula that it does. Now let's take a look at carbon dioxide, another very common substance. Carbon has 4 valence electrons, they're all unpaired. Oxygen has 6 valence electrons, only 2 unpaired. Carbon atoms will form 4 bonds because they need 4 electrons. Oxygen atoms normally form 2 bonds because they need just 2 electrons. So here we go. Here's this carbon, here's the oxygen, here's the other one. So I can share this pair, and I can share that pair. So we wind up with 2 double covalent bonds within the CO2 molecule. So we have 4 bonding pairs of electrons and 4 lone pairs. Let's draw out CCl4. So we put carbon in the middle because carbon needs the most electrons. We'll go back here, do it slower. Here's carbon in the middle. Down it and try it again. Here's the carbon. Here comes the chlorine like this. All right, here's my other chlorine coming in from the bottom. One from the top. There it comes. All right, a lot of dots here. Okay, and I can't circle, 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 circle. Okay, there's my 4 bonds. So it will look like this. We replace the bonding pairs with dashes. And here I go. There's my CCl4 molecule. 4 bonding pairs, 12 lone pairs. Now how about NH3, which is ammonia? Put the nitrogen in the middle. Here comes a hydrogen here. Another one in here. And here comes the last one. We circle the bonding electrons. And we're going to replace them with dashes. And thus we have 3 bonding pairs and 1 lone pair. You can summarize all of those for these guys. Here we go. We have CH4, NH3, and H2O. CH4 would be the same as the CCl4 that I did earlier. So we have electron dot structure. We have what we'll call a Lewis structure, our structural formula. And lastly, we have molecular models. They all kind of show the same thing. So it's good to know how many bonds atoms will form, and there are some patterns we can follow. For instance, group 7A, they only form 1 bond normally. 6A, just 2 bonds. You notice it goes 1, 2, and then 3, and then 4. These are all non-metal side. Boron is a funny one. It's right above aluminum. It forms 3 bonds. It's kind of an oddity like that. Hydrogen just forms 1. Normally, it's these here that you have to remember, and the hydrogen. And you're going to see boron very much. All right, so let's say we wanted to determine the simplest formula for a compound that consists of just carbon and bromine. So you'd ask yourself some questions. How many bonds did the elements form? Carbon forms 4 bonds and bromine 1. How many atoms are we going to need then? We're going to need 1 carbon and 4 bromine. See how the numbers switch? What's the formula then? CbR4. So, and you might wonder, how do we know which order to write the elements into the formula? Normally, and again, there's all sorts of exceptions with this, but normally we write the element first that's to the left of the periodic table more than the other one. Now, when you name covalent compounds, we're going to have to use prefixes because they can form various ratios with each other. So some of these you should know. For instance, you should have seen from penta down through deca anyway. And tetra is the one you might not remember. You may or may not know mono, but di and tri are kind of obvious. So, mono is only used for the second element in a formula. It's just never used for the first. Now here's an example. 2 compounds that both contain carbon and oxygen. Carbon monoxide and carbon dioxide. Why don't you try to name these 2? So you can pause for a second and try to name them. Or here are the answers. SO3, sulfur trioxide. Now the next one, you're going to have to say that there are 4 phosphorus and then 3 sulfide. So that's tetraphosphorus trisulfide. Now here are a bunch of them that you can look at and you can see the names and how they match up pretty easily. These names are pretty easy because you're really spelling out the formula. SO2, sulfur dioxide, silicon dioxide, SiO2, SF6, sulfur hexafluoride, and it gives you the different uses for them.